the problem reads as use geometry to evaluate the double integral over the region R of square root 1 minus x squared dA, where R is this particular region with the x interval from -1 to +1 and y interval from -2 to +2. Now this problem is essentially asking us to calculate the volume underneath this surface square root 1 minus x squared, and the way we can interpret this surface is like by setting z equals to square root 1 minus x squared, and because this is up the positive square root, this means that z is greater than or equal to 0. So now we will square both sides to get z squared equals to 1 minus x squared. Now this is just x squared plus z squared equals to 1, where z is greater than or equal to 0, because otherwise it won't satisfy this equation. In order to satisfy the first part, it must mean that this is a semicircle on the xz plane. This is the equation of a semicircle on the xz plane. So we will draw a semicircle here. Excuse the drawing. So if we change y, or what's going to happen? Because there is no y dependence on this equation, this means that this figure is simply going to repeat itself as we move along the y-axis. This means that we'll have infinitely many semicircles which will collectively form a half cylinder, and it will look like this. Now let's define our regions. X starts from -1 to +1. The -1 is somewhere over here, and this is where we end our x coordinates, the x interval. And similarly, y equals to -2. This part is over here somewhere, covered by the solid, and y equals to +2 is where we end our y interval. This defines this rectangular region. This is on the xy plane, this red figure. So the question is asking us to do is actually find the volume underneath this surface, because this surface is z equals to 1 minus x squared, and onto this region R, this rectangular region. So we know that this is a half cylinder, which means that we can use the geometric formula for the volume of the half cylinder. So what is the radius of the cylinder? We know from the equation of this circle that this particular circle, this particular slice of the cylinder, must have a radius of 1, because x squared plus z squared equal to 1 squared, which is just 1. So this radius is the radius of the cylinder is also 1. And therefore the volume of this cylinder is just, since the volume of a cylinder is pi r squared h, the volume of a half cylinder must be half pi r squared h. So we need the height of the cylinder, which is just this particular line. This means that since this is in the y-axis, and y is -2 over here and +2 over here, this means the height is actually the length of this line, this green line. So the height equals to +2 minus this endpoint -2 minus -2, which is equals to +4. hence the volume is half pi, the radius is 1 squared times 4. So 4 by 2 is just 2 and 1 squared is just 1, so this is nothing but twice pi. And therefore the integral, the double integral over this region of 1 minus x squared dA must also be equal to twice pi. Now we will use iterated integrals to solve some of the problems. Iterated integrals are simply the right hand side of Fubini's theorem. Now Fubini's theorem, in the last video we have applied Fubini's theorem on 3 different circumstances. One was on type 1 region where we did the y integral first, and this is the right hand side of the Fubini's theorem applied on the type 1 region. So this part in the box is an iterated integral. Similarly, Fubini's theorem on the type 2 region is this box, and only the box is the iterated integral on the type 2 region. And for rectangular coordinates, we have found that these two integrals are actually equal, and both of them are iterated integrals. The main concept is that we have to write both the x integral and the y integral instead of having dA. So now let's solve a problem. Let's do the a integral first. Here we have to do the y integral first, treating x as a constant, which is applying Fubini's theorem. So here x squared y squared divided by 2 dx, and we have to take the limits from 1 to 2. These are the y limits. This must be equal to two squared minus 1 squared dx. 2 squared is 4. 4 times 4 minus 1 is just 3. So we've got 3 by 2 x squared dx. Once we do the x integral, we'll get x cubed. So 3 by 3 goes out. So we got half x cubed 3, 0, the limits. Now once we substitute the limits, this should be 3 cubed is 27, 27 by 2 minus 0 cubed by 2. 0 cubed by 2 is just 0, so we're not going to write down. This is the answer for doing the integral in this way. We can do the same integral in the other order. Now we're doing the b integral. So now here we simply change the order. First we do the x integral. So this should be x cubed divided by 3 times y, and then we take the limit 0 to 3 dy. X cubed, so we put 3 cubed by 3 minus 0 cubed by 3. This is just 0. So you got, this is 3 squared, so you got 9y dy. This means that this is just 9 by 2 y squared. I will take the limits from 1 to 2. 2 squared is 4. 4, and we subtracted it, 1 squared is 1. So it's 9 by 2 times 4. Sorry, this is 3. So 3 into 9 is 27. 27, and we have on the denominator 2. So it's 27 by 2. Either way, we get the same result. Let's do another problem. We have to evaluate the double integral on the region R of x minus 3y squared dA where R is this region written in set builder notation, where R consists of all the points x, y, x comma y, where x coordinate is in between 0 to 2 and the y coordinate is in between 1 to 2. And we can write this as well, write this as 0 to 2 cross 1 to 2. Now this is the graph of a three-dimensional graph of z, and this is actually z equals to 0. Z equal to 0 is the xy plane, and you can see that the surface actually lies below, not above, below the z equal to 0, or below the region R. The region, it lies below the region of integration, and therefore this volume will come up as negative. Like once we do the integration, we'll have a negative value, and z obviously decreases as we go downwards. So let's try with type 1 first. We're told to use both type 1 and type 2 to evaluate this integral. Now we apply Fubini's theorem for type 1 integrals, which means that we do the y integral first. Now this region has the y bounds, this one 1 and 2, so y varies from 1 to 2. X minus 3y squared dy, and x varies from 0 to 2, also written here. As this is a type 1 region, we have to do the y integral first. So we do this, and we treat x as a constant while doing this. So we get xy minus 3 by 3 is just 1, because so we get y cubed. Now we need to take the limit from 1 to 2 dx, and it's just twice x minus 8 minus, and we put 1 in place of y, x minus 1. Now twice x minus x is just x, and we have got minus 8 plus 1, because minus and minus is plus, so we have got plus 7, sorry, minus 8 plus 1 is minus 7 dx, and this is just x squared by 2 minus 7x, with the limits from 0 to 2 should be 7, 2 squared is 4, 4 by 2 is just 2, so we've got 2 minus 7 and 2 is 14, and minus 0. So we have, the answer is 2 minus 14 is minus 12. Minus 12 is the value of this integral, and as expected, this is negative because our surface lies below the region of integration R. Now let's do the same problem using type 2 regions. X minus 3y squared dA So our x limits, we'll do the x integral first as it's type 2 integrations from 0 to 2. The y limits are from 1 to 2. You write down the function. And we do the x integral first, then y integral. This will be x squared by 2 minus 3xy squared. The limit is taken from 0 to 2 dy. So we put 2 over here, we get 4 by 2 is just 2 minus, put 2 over here, 3 into 2 is 6y squared. And if we put 0 squared or 3 into 0 into y squared, both are zeros. So the 2 0, sorry. Now we do the y integration. Twice y minus 6 by 3 is just 2y cubed. This will be 4. 2 into 2 is 4 minus 2 cubed is 8 times 2 is 16 minus 16 minus 2 into 1 is 2 and 2 into 1 is also 2. So we got 2 minus 2 into 1 cubed is 2. 2 minus 2 is just, this is just 0. Since this is just 0, that means we have again 4 minus 16, which is minus 12. We get the same answer as expected. Now let's do another problem. Here we have the double integration of y sine xy times dA over this region. X varies from 1 to 2 and y varies from 0 to pi. And this is the graph of this particular function of z equals to y sine xy. Here we have both positive volumes and negative volumes. I'm using the term negative volumes to indicate volumes beneath the plane z equals to 0 or the xy plane. So let's call this volume V1 and this volume V2. The integration will actually give us minus V2 because this is below the xy plane, and the integration will give us plus V1 because it's above the xy plane. So the integration y sine xy dA is equal to V1 minus V2. So the integration is actually giving us the difference between the volumes, and let's see what the integration gives. First, let's see what happens if we try to integrate it with type 1 integration, meaning that we'll do the y integration first. Now this is at pi because y starts from 0 and ends at pi, so this line is from 0 to pi. 0 to pi is our y limit. We do the y integration first. Y sine xy, and then we do the x integration. X varies from 1 to 2 or here. Now note that this is a type of integral y times, once we consider the inner integral only, y times sine some constant, because as we're treating x as a constant, some constant times y. This has to be integrated by parts, so this will actually involve more work than if we do type 2 integration. Let's see what happens if we try to do a type 2 integration. We do the x integration first. The x limits are from 1 to 2 here, and the y limits are from 0 to pi. We can take it from the graph or the question if you want. And y sine x comma y dx times dy. So we're not going to do this. This is more work. And instead we do the type 2 integration. Now note that this is y is being treated as a constant in this integral. So a constant times sine x times another constant. This is just like a sine bx sort of integral, which is very easy to evaluate. This will be y divided by y cos xy, and of course it will have a minus sign because the integral of sine has a minus sign. And we already did the x integral. We also have to substitute the limits dy. So let's do the limits. This is minus 0 to pi. This is just 1. Y by y is just 1. And we put in 2 now. So we get cos twice y minus cos y dy. So now we just use the linearity property of the integral, which means that we can split it up with the sum. Minus minus is plus. Integral of cos y is minus half sine twice y from 0 to pi, and this is just plus sine y from 0 to pi. This will be sine twice pi minus sine 0. Both of them are 0, so this is 0. And this is sine pi is 0, and sine 0 is also 0, so it's 0 minus 0. This is also 0. Sorry, this will be minus sign. So this is minus 0 plus 0 is also 0. This means that the volume here and the volume here are equal. In other words, V1 is equal to V2. There is equal volume above the xy plane and equal volume below the xy plane. Let's do another problem. Find the volume of the solid S that is bounded by the equation z minus sin x cos y equals to 0 and the planes x equals to pi by 2 and y equals to pi by 2 and the 3 coordinate planes. So let's first start with this equation, which says that z minus sin x cos y equals to 0, and this must mean that z equals to sin x cos y. Sin x cos y is actually this surface over here. Next we move on to the planes x equals to pi by 2. So here is x equals to pi by 2. And x equals to pi by 2 gives this particular plane. Next we have y equals to pi by 2. Y equals to pi by 2 will give me this particular plane. Then, and the 3 coordinate planes. The 3 coordinate planes are just the first. Let's start with x equals the xz plane. The xz plane is this. The xz plane. The xz plane is this one. The z. The zy plane is this one. And finally, the last plane, xy plane, is this gridded plane. As you can see, this surface is entirely trapped by these bounds. It's inside this box shaped thing. And here we can use a concept known as separable functions to solve our problem. And let's first see what a non-separable function is. It is any function which cannot be written as a product of functions which depend only on one variable. So it cannot be written like this. An example is sin xy. This cannot be written in this particular form. Now, a separable function is any function which can be written in this form: g of x, h of y. And is our function separable? Let's see. Z equals to sin x cos y, and if we let g of x be sin x, this depends only on x, right? So this is okay, and cos of y only depends on y. This means that our function is separable. Let's say we have a separable function f of x comma y, and we want to take the integral over a rectangular domain. Then we can write this write f of x y as g of x times h of y, because it is separable, times let's take a type 1 integral. It doesn't matter, as the region is rectangular. You can do either way with the same limits. Let's define our rectangle in this way, that the x coordinate varies from a to b and the y coordinate varies from c to d. So we have the x limits, so it should be a dx here, from a to b. The y limits should be from c to d. Since g of x is actually a constant while we're doing the y integral, the inner integral, we can take it outside our integral. Now let's think about the thing inside the parenthesis. What is this thing? So this is a definite integral with constant limits, so in terms of y only, and this is definitely a number, right? And the number is going to be, this is a non-varying number, it won't change, it's a constant, it's just any other constant. So a constant can always be taken outside of the integral, the x integral, we can take it outside of the x integral. So when our function is separable and we are doing the integration on a rectangular domain, we can simply split our integral into a product of two definite integrals of one variable. Let's see this problem in action. So we have our region R and the function is sine x cos y dA, where R is this particular rectangle in the xy plane, where x goes from 0 to pi by 2 and y goes from 0 to pi by 2. So since this is a separable function, we can write this as the product of two definite integrals. One is in terms of x. We don't really have to write y first and x later, we can do it the other way as well, doesn't matter. Now we write down the limits. In this rectangle, x is varying from 0 to pi by 2, y is varying from also varying from 0 to pi by 2. And this is just minus cos times the integral of cos x is sin x cos pi by 2 is 0, cos 0 is 1, so we have got 0 minus 1 minus minus 1, because cos 0 is 1, we have a minus over here, and this is the lower limit, so we get minus minus 1. Next, sin x, sin pi by 2 is 1 and sin 0 is 0, so 1 minus 0. So this basically this is 1 because minus minus is plus, so we get 1 into 1 is just 1. This means that this integral or the volume is actually, our required volume is equal to 1. Next problem is quite interesting. We have to find the average value of this particular function, and our function is the same function as before, sin x times cos y, and the interval is also the same. X varies from 0 to pi by 2, y varies from 0 to pi by 2. So how can we find the average? Now here it mentions that given that the average value of a function of two variables is the function's average value is 1 over the area of the region R, where AR is the area of the region, and we then take the integral over the region R of f of x comma y with times dA. So we already know from our previous problem what this is. This is in fact equal to 1 from here. Sorry. Since this is equal to 1, we just need to find what A of R is, the area of the region. Since this is a rectangular region with, let's just draw the just the two-dimensional diagram of the region, the x-axis and the y-axis. X varies from 0 to pi by 2, y varies from 0 to pi by 2. So this is our rectangular region R, and this is actually a square because both lengths are equal, and the area of this thing will be just the product of the sides. Pi by 2 times pi by 2 is pi squared by 4. Hence the average value of my function is equal to 1 by A of R this is A of R is just pi squared by 4, and this particular double integral is just 1 here. And so we have, so we just flip this over, we've got 4 by pi squared. This is our average value.